This is AP Calculus, Unit 1, Lesson 5. We're talking about the intermediate value theorem and the extreme value theorem. And I got lazy for my title. I also got lazy for my unit guide. But that's what we're on. We're finally on continuity, standard C, although I was talking about how we kind of did continuity yesterday. So I want to make sure that we know how to talk about graphs correctly. So we have this parabola with x coordinates A, B, and C. So if I come straight up from A and I intersect this graph at this point, how do I say what that point is? We should, and I'm going to assume that this red function here is f of x, not g of x or h of x or anything like that. So how do I talk about that point? And I'm just going to do it, and then you guys can do the next 2 points. This point right here is a comma f of a. F of a also means what again?
The height of a.
Height of a, perfect, yeah. All right, so go ahead and label this point and this point, the points above C and B. All right, and I'm going to write them up here silently. All right, and then we know, of course, also that if we come out to the left of here, that height right here is what?
The limit?
Not quite a limit. I'm just asking for what is the height of this point. So what do I say, or what do I write for my notation? The height of A is f of A, exactly. And I guess my A and B were really close to each other, so this would also be the height at B if this was the same height. And then up here, what do I write for my notation? F of C, and that translates as this f of C. Another way of saying f of C is height of C. Perfect. Height of C. So it's finally in the notes, we start calling that height. All right, so what do A, B, and C mean? Because we're going to see these in a bunch of theorems coming up here, and I just want to make sure that we have a visual example. A is always going to be your left endpoint. Left endpoint. Usually in our theorems we'll say, okay, assume you're in a certain range from here to here. Our range is usually going to be from A to B, so B is going to be our right endpoint. Right endpoint. And I'll say choose a C between A and B. C can be anything. I just chose it to be the vertex in my example up here, but I could have put C here, I could have put C here, I could put it here. It doesn't matter. I just want C somewhere in between A and B, but not equal to them. So this is just some certain point. So when I now say choose a certain point, immediately in your head you're like, oh, I'm going to make that variable C, and it'll be matching everything that I've learned in class. All right. So this is kind of important. I wish I made my graph slightly smaller because I wanted this on the same slide. So if you could write this underneath, I'm going to write it up in the top right. I want this in red, star this. This is going in our summaries. What is a max? What is a min? What does that mean in notation? A max and a min. So max means that f of C is always, always, always greater than, I guess, or equal to f of x. How do I read this? This is saying that the height at a certain point, at some certain point, is always greater than or equal to the height of the rest of the other points. X is all of the other points. I can choose anything for x, but C is some certain point. I'm now saying at a certain point, the height is greater than all of the other points, therefore the height is the maximum. All right, what are we going to do for minimum then?
Same thing, but less than or equal to.
Same thing, but less than or equal to. An arrow. Try to say this in words, not notation. I don't want to hear f of C. What does this thing mean? F of C means?
Height of C is less than or equal to the height of everything else.
Exactly, yeah, perfect. Well said, good job. All right, let's go on to our next slide. Making sure that we have all that written down. And here we go. Okay, I want to talk about types of intervals. types of intervals. There are two types. There's closed and open. What do they look like graphically? What do they look like in notation? Let's talk about the graph first. So let me set up a quick little, it doesn't have to be very big because it's just kind of going fast here. And copy paste to go faster. All right, we have two lines. And I'm always going to have an A and a B. So I'm going to make my A over here, my B over here. We'll do the same thing over here as well. My A is going to be here. My B is going to be here. All right, so for a closed interval, if I have some squiggle, I'm trying to do the same squiggle over here. Close enough. If I have some squiggly function that is on a closed interval, these are intervals here. On a closed interval, the endpoints are closed. Both of them are closed. Closed points. And by default, the open interval has, oh, exactly, open points. Oh man, who would have thought? And if you have one of each, then I have no idea what you'd call that guy. But in calculus, we usually always have open or always have closed, depending on the type of theorem that we're talking about. All right, so for all points, x is all points, that has to be between B and A. I usually have left and right, okay? So I'm going to have less than signs. Are these less than signs or less than or equal to signs? You have to choose which one goes with which. Should these have the equal signs or should these have the equal signs? The right or the left have equal signs? The left, yes, because I can be equal to those points. If I have the wall test, my wall will pass through the point. I can be equal to that. Perfect. Another way of writing this, this is the, I think this is compound notation. I'm also forgetting my stuff from last year also. But this is using inequalities. There's another way of writing it where you just do interval notation. So A comma B, A comma B. One of these has parentheses, one of them has brackets. Which one goes with which? Do we remember?
I think brackets is if it includes the point.
You're correct. Brackets includes the point, parentheses does not. We have two more slides. All right, finally, the intermediate value theorem. Once you've written it out once, it is enough for the rest of your life. Just call it IVT from now on. Too much writing for a mathematician, right? We're lazy. All right, so we're going to make a graph. We're only going to be really talking about the right-hand side of the graph. We don't really care about the left, but there are my axes. All right, so let's draw a function. I don't know. Function looks like this. Bloop. And let's choose my A. We'll say this function goes on forever and ever in both directions. My B, just talking about this area of the graph. And I need to state my theorem here. Just making sure I do this correctly. Let's choose our C to be just the x-intercept. C. All right, so things that we need so there are a list of requirements. So you can say requirements or need, whatever you want to write. Need is shorter, so I'm going to write that. In order to use this theorem, we need one thing. We only need one thing. Some other things will need three things. We need continuous. If we have continuity, then we can use IVT. So what does IVT basically say? And I'm going to write it in green over here on the side. It basically means that the value, I'm putting that in quotes, or the height f equals y. All of these things mean the same thing from now on. Usually I'll be talking about height. Sometimes you'll see f of something. Sometimes you'll talk about the y-coordinate. This theorem basically says that if f, okay, this is going to be in red here. If f of a is positive, so I'm going to say greater than 0, and f of b is negative, less than 0, then there exists at least one point, some point needs to be, do you want to guess at what it is? Some point has to have the height of 0. Perfect, yep. In this case, it happened to be right here. If I have a positive and a negative, and you can flip this on its head too, if I go from a negative to a positive, there has to be at least one height that's 0. The message of this is pretty straightforward. I have to pass through all points in this interval. So this is part of it, but IVT says a little bit more. You pass through at least all of the points between here. So all of these heights between here and wherever this B is on the right, this height, f of a, oh wait, sorry, a is right here. So this height here, f of a, this height here, f of b, the values, or the heights, all values are passed through in these points. That means if I look at some height right here, I have to go through that height because it's between these two heights. I don't have to pass through this height. It's not through those two heights. Pretty straightforward. I don't have to pass through this. I do have to pass through this height. At least once. I might pass through it multiple times. So IVT more generally, and god darn, I keep running out of space, passes through all heights between f of a and f of b at least once. It could pass through it twice, thrice. It could have like a sine wave function and you have that height multiple times, once and twice. But you're guaranteed at least in that interval, you'll go through those heights. So far, so good? All right, IVT, done. Next, EVT. You write it once, you're done. On the AP exam also, you just write EVT, they know what you mean. Extreme value theorem. EVT. We need another graph. Again, I only really care about the right-hand side, but let's get our axes set up. Let's have a function that looks like kind of a sine wave type function. And I'm going to choose my A there. Let's choose the B, I don't know, somewhere over here. It doesn't really matter. All right, extreme value theorem. Let's start with the things that we need. The requirements. In order to use extreme value theorem, you need now two things. One, you need continuous. Second thing that you need, closed interval. And I'm going to underline closed because the word interval usually doesn't come up. Closed interval. So that means that these points have to be filled in. They have to exist at those points. Okay, what does EVT say? EVT says this. So if, I guess I should have done this the same way on the last one. If a function f of x has the needs, is continuous, and on closed, or I should just say, and on a, b, you know it's closed because I use square brackets, then there exist these two things. then f of c, I'll define this informally in a sec. F of c is less than or equal to f of x. This thing exists, and f of c is greater than or equal to f of x exists. It only says they exist. It doesn't even say where. It just says, hey, they're there somewhere. Go ahead and look for them. I don't care. What does this thing mean again from our last slide? Or 2 slides ago, I should say. What does this thing right here mean? I just defined it 2 slides ago. Go back and look at your notes. What exists? Oh.
There are heights within the range that are both greater and less than A and B.
Close. You're not exactly saying the word that I'm trying to listen for. Look up on the screen. These guys. This is the definition of maximum. This is the definition of minimum. So this theorem is essentially saying, if I have a continuous and closed interval, then a minimum and a maximum exist. So if continuous and closed, so EVT guarantees min and max. It doesn't say where they are, it just says that they exist. It's a pretty loose theorem just to say something exists. And it exists at some point C, but we don't know where that is. And we can look at this function too. Well, yeah, a minimum does exist. There's a minimum right there. Where is the maximum? It's hard to say because that's almost a flat line, but the maximum is somewhere right there. All right. There are a few kind of trivial examples that I wanted to go over, but we ran out of time. Like, what about a flat line? Doesn't that have a minimum and max? They happen to be the same thing. Minimum and the maximum are both the same. And they exist at every single C that you can think of. But stuff like that, pretty fun to think about. So we have EVT, we have IVT. Let's do our summaries and then homework.